Hello everybody, this is Jenness, and today we're going to talk about running tools in ArcGIS. We call this geoprocessing, so we're going to be talking basic geoprocessing, how these tools work. We're going to be talking about models and environments and ways to automate tools. Now this lecture is fairly long, so I think we'll break it up into 4 different sections. First one, we're going to talk about general geoprocessing. Then in a separate video, we'll talk about environments and then model builder, and very brief look at Python. Python's a neat way to run these tools, but it's a fairly large topic, so we're just going to kind of introduce you to it in this class. This particular video will be about general geoprocessing, covering what it is and what it means in the GIS world. And in ArcGIS, a geoprocessing tool is basically a tool. All their tools are geoprocessing tools. So when you ever hear that term geoprocessing, they're just talking about running a tool. There are a lot of them in ArcGIS. As the latest version, I count over 1,000. So you got plenty of tools to work from. Now, we can run these tools in a number of ways. First off, you can run them just individually. You click one of those tools, fire it up, fill out the form, and hit go. That's probably the way most of us do it most of the time. You can also string these tools together in models, and we'll get to that later. But the neat thing about this is you can create a model where a tool produces an output, and then that output is used directly as input into the next tool. You can string a whole bunch of them together to do fairly complicated tasks. And then finally, you can run these tools in Python, and yeah, we'll cover that a little bit as well. Now, in this particular lecture, I showed you there's well over 1,000 geoprocessing tools available. I'm just going to show you some of the most common, basic, and original tools. These vector tools I'm going to show you here go all the way back to the beginning of ArcGIS, back in ArcInfo days in the 70s and 80s. Still popular tools and very useful. So I'm going to explain to you what the buffer tool is, the clip tool, intersect tool, an identity tool, a union tool, an erase, symmetric difference, merge and append, and dissolve. Now in the lab for this lecture, we're going to practice just the buffer, clip, union, merge and append, and dissolve tools. All right, leaping right into it, what is the buffer tool? It's about what you'd expect. You take an existing vector feature, you say you want to buffer it, and you get a new polygon feature class that shows everything within a defined distance of those original vectors. So in this picture we had some roads. We were curious what the area within a half-mile of roads looked like, and so we generated a half-mile buffer. Easy to do. A neat thing about polygon buffering is that you can actually buffer them with a negative distance. So you can buffer on the inside. So in this example you see that there was an original stand there. We did a negative buffer and we get a polygon that shows the internal part of it. The clip tool is a really useful tool, especially when you're trying to analyze a set of vector objects that are within some defined area. So for example, in this picture I have the Coconino National Forest in green. I have a lot of roads in the background, and I'm curious some characteristics of the roads within the Coconino National Forest. Now you could just select those roads that intersect the Coconino, but you run into a problem because so many of these roads extend past the Coconino. They go outside, and so when you start calculating statistics on them, you wind up calculating stats on a lot of roads that really don't apply to what you're interested in. So in this case, the solution is to clip the roads to the Coconino Forest, and that's what this tool does. As you can see, it produces a new data set where everything is just snipped off like the Coconino is a cookie cutter, and we're left with the roads inside the forest. The intersect tool is another useful tool. It's useful for taking two feature classes and finding those areas that are common to both feature classes. So in this example right here, we're looking at we're looking at one feature class here. It has 2 polygons. We have another feature class here with 2 more polygons. When we intersect them, we get a new feature class that has the common areas that existed in both polygons. Now, notice the outside of it. These areas only existed in one of the original feature classes, and so those are clipped out, and they do not make it into the Intersect feature class. Now, down below you can see that the Intersect tool also applies to other shape types than polygons, so we can intersect 2 polylines, and again we find out a new polyline feature class that is only that portion that existed in both original polylines. Oh, and as we discuss these, a few of these here, I'm showing slides that show what happens to the geometric objects when you run the tool, but you should also be thinking what happens to the attribute fields, attribute tables, and attribute values. When you run these tools, Intersect, for example, you give it a couple of feature classes to start with, you get a new feature class at the end. And the geometries look like are visualized in this slide, but now we have to think about if the first feature class had a particular set of attribute fields and the second feature class had a different set. Well, that means your new intersected feature class is going to have all the attribute fields that came in from each original feature class. Now this is a little tricky and complicated, so let's look at it in action here. So, for example, we have a feature class called rectangles. Here's where they are. We have another feature class, I'm calling it rectangles 2. That's them. We run the intersect tool and we get what we expect. Now this is fine as far as the geometries go, but now I want you to understand, and this is important to understand, what is going on with the attribute values. Right, here are the various attribute tables. Right here is the attribute table for rectangles 2, that's the red ones. This is the attribute field for the first rectangles, and this is the attribute field for the intersected output. Now we have in rectangles 2, the red one, we have one with a horizontal name of Thelma, another one a horizontal name of Louise. Then we have a rectangle ID field of 3 and 4. Go to the other one, this is the blue rectangles. We have Tom and Jerry and the vertical name and a rectangle ID value of 1 and 2. Now what I want you to notice here is that the 2 original feature classes, they each have a name field and an ID field, horizontal name, rectangle ID. The trick here is that the name field is different between them. This particular feature class, rectangles 2, has a name called horizontal name. This feature class has a attribute field named vertical name, so they don't have the same value. Now, they both have the same field called rectangle ID, so in this case the attribute fields are named the same. Now what happens in the intersection? So in the intersection field we have, in the intersection feature class, we have a horizontal name field, a rectangle ID field. This comes from this one and this one. Then we have a vertical name field and another rectangle ID field. It comes from here and here. Notice that we have 2 attribute fields with the same name, rectangle ID in both. Now you can't actually have 2 attribute fields that have the same name. So what's happening here is the tool is producing attribute fields and then giving it something called an alias. So in this case, the field name isn't actually named rectangle ID. If we right click on it and go to properties, we can see that the actual name is rectangle ID _1. So it's given it a name to guarantee that it is a unique name. Then the alias, what it just shows you in the table, is rectangle ID. If we look at this one, right click and do properties, we said that its actual name is rectangle ID. So the point here is that it produced a new feature class with all the various attribute fields that existed in both original ones. And then for this particular one, for the rectangle ID one, it actually had to change the field name in order to put it in legally. Now, it added all the original fields and it added all the original values. So if we look at the intersection region, if you remember, this in the red feature class, this is called Louise. In the blue feature class, the vertical one, this is Jerry. Well, this particular one is Louise and Jerry. It's the intersection region. Let's turn that. So this one has all the original values from both features. So yeah, this like I said, it's a little complicated, but it's really important that you understand what is happening with the attribute values and how the original attribute values are transferred into the new intersection feature class. The identity tool is an interesting tool. It sort of stamps in features into an existing feature class. So you have this existing feature class that you see on the left here. You might have some new regions that you would like to integrate into your feature class, and the identity tool just sort of stamps it in there. The new feature class that you get after running the tool will have all the same regions that the original feature class has, and any of those original regions that overlapped your identity features will just be stamped right in there. Let's look at an example. All right, so we'll start with these horizontal rectangles again down here near Fisher Point. Suppose I have some features in the background that I just want to stamp in there. I made some just hexagonal polygons just to demonstrate this idea. So suppose these hexagons represent something we care about, and we just need to know how these hexagonal regions are distributed within our original rectangles. We just sort of want to stamp these boundaries in there. We run the tool and we get this. And sure enough, notice that this new feature class contains all the spatial regions that existed in the original rectangles, but just has the hexagonal polygons sort of stamped in there. So the geometry is easy enough to understand, but it's again really important to know what is going on with the attribute values. Here are the attribute tables for the respective feature classes. Here's our rectangles. Again, we have Thelma on top, Louise on the bottom. But we also have these hexagons. We have hexagons named A, B, and hexagon C. Our new feature class, that is the identity feature class, is, let's turn off the hexagons there. The new one has 6 polygons, and if we select all the Thelmas, we sure see again that they are the ones on top. Select all the Louises, they are the ones on the bottom, just like we expect. But we also have the hexagon region stamped in there. So hexagon A is down here, hexagon B, sure enough, is this part over here, and then of course hexagon C right in the top. Now notice that there is a polygon over here that did not exist in the original hexagonal feature class. I'll turn that back on. So this polygon right here, did not exist. And sure enough, it has no value in the hexagon name attribute field. The union tool does something similar to the intersect as well, except remember the intersect only produced features in which overlap the original source feature classes. The union tool will bring in all regions that existed in all the source feature classes. So in this case we have 2 feature classes that overlap, but only the middle part of it actually exists in both feature classes, but we still get all the little pieces. we get the top here and the edges, these regions that only existed in one of the source feature classes. Well, those still pop out in the new union feature class. Okay, back to our demo. We'll look at what union does in both geometrically and with attributes. So we start with our same two sets of rectangle polygon feature classes. We run the union. Sure enough, we get a new feature class that contains the full area from all input source feature classes. Alright, so simple enough geometrically, but what's going on with the attribute values? Alright, here are our rectangles and rectangles 2, the originals. We have Tom vertical here, Jerry vertical here, Thelma, let's get rid of that, Thelma horizontal here, and Louise horizontal here. And then we got our new feature class with all the union regions. Okay, so now we look at what's happening with our new union feature class. We look in the attribute table, we see we have 8 features, 8 polygons in the new union feature class. We look down here, it looks like there's actually more than that. We have 2 along the top, 4, 4, and 2 more, which should add up to 12, not 8. But this is an interesting function of the union. Turns out that if you select this feature class, this feature, you get 2 polygons selected. Same with this, same with this, same with this. That's because they are just a single polygon, but they're a multi-part polygon. Just the way the union tool works. And the interesting thing about this is that these, if you remember, these are objects that only existed in one of the original feature class. So if you click on one, you see that it has the Tom values from the original vertical Tom rectangle, but no value in the Louise, because that did not exist in the horizontal rectangles. If you select all of these horizontal, sure enough you get all of the Toms. Select all of these were all of the Jerrys in the vertical rectangles. Now right across here, these were all the Thelmas in the original horizontal, so we select those. Sure enough, they all got Thelma in there, and this, sure enough, all Louise. So the trick here is to understand that all the attribute fields and all the attribute values got transferred over. The regions that only existed in one of the original feature classes, though, have no value in these attribute fields that correspond to the other feature class. So a little tricky, but important to understand. The erase tool is pretty intuitive. You use a feature class to just erase portions from a source feature class. So in this case, you just sort of erase it out from the center of the original feature class, and you're left with just those parts that existed outside of the erase features. Symmetric difference is an interesting one. It's honestly one I rarely use, but it's been there since the beginning, and so you ought to know about it. It's sort of the opposite of the intersect. If you remember, the intersect tool returned a new feature class that consisted of the areas that existed in both source feature classes. Well, symmetric difference returns everything that only existed in one of them and just erases everything that existed in both. So like I said, I've used it rarely. The only time I ever used it was an instance where we were curious about jurisdictional boundaries from law enforcement agencies, and we were working on a project where people would call a 911 from their vehicles in California, and the task was to figure out which law enforcement agency had jurisdiction given the location of the phone call. Now the problem there was that there were a lot of law enforcement agencies that had overlapping jurisdictions. So one particular spot might have the call should go to both the Sheriff's Department and Forest Service. So we use this Symmetric Difference tool to find those regions that only had a single jurisdiction, and that just made our task easier. That's the only time I've ever used this tool, but if you have a good example of it, please let me know and I will use it in future lectures. Now, merge and append are both simple tools. They don't do any geometric operations at all. All they do is combine the original feature classes into a larger feature class. So if you had one feature class that had 5 features and another feature class that had 6, you just get a new feature class that had 11. Just adds the new features as separate rows in the table. The only difference between merge and append is that merge combines them and makes them into a new feature class, while append takes a bunch of features and adds it to an existing feature class. Otherwise, they're pretty much the same tool. I have noticed, though, that append crashes a lot. Merge is pretty reliable. So, yeah, merge is stable. Dissolve is a very popular tool, very useful. It combines geometric objects based on attribute values. Well, mostly. You can combine every geometry in a feature class into one single merged object, and then in that case it ignores the attribute values. But more often you will dissolve based on some common attribute value. So in this example, you see I have a county map showing all the counties in the 4 corner states. Well, I can dissolve this county feature class based on the attribute field state, and so all of a sudden I have 4 state polygons left over. So it just dissolves all the Arizona counties into one object, etc. Really useful tool. I use this one all the time. Now, a quick question, just to think through some of these tools. Suppose we have a stand polygon like you see here up in the top, and we want to produce a new feature class that contains just this outer ring of that original stand. How would we do that given these tools? It would take a few steps, but what do you think? Now, hopefully you're thinking through this, but what I want you to think about is, first you could do a buffer on it, but using a negative buffer. That will give you a polygon that represents that internal region. And then you would use the erase tool to erase that internal polygon from the original one, and that would just leave you that outer ring. And that's how you do it. Okay, and that's what I'd like to say about general geoprocessing tools. So we'll close off this video with that topic. The next video will be all about environments, which are important ways to modify the way you run tools. All right, thanks so much.